In this lecture, we're going to begin our coverage of what's referred to as central tendency statistics. And so basically, when we talk about central tendency, what we're trying to do here is calculate one number that will provide a summary of the entire sample of scores. And measure, as the term suggests, the measurement of central tendency provides an indication of how one person's score, where it resides with respect to the sample or a population of interest. And so the measure of central tendency that summarizes this location will actually eliminate the need to examine every single score. And there are three measures that we will cover: the mode, the median, and the mean. In terms the mode refers to the most frequently occurring score in a distribution, and in a distribution is identified as the quote-unquote highest point in the frequency distribution. So once again, as we reviewed in Unit 1, here along the x-axis is the dependent variable, some score, while the number of occurrences of that score is plotted along the y-axis, and we see here what we'll define shortly in this video as a normal distribution. And the mode represents that score of the dependent measure that occurs most frequently. There are some distributions that are different than the normal distribution, and that is one example is what's called a bimodal, bi for two. So in this case, we see a distribution of scores, but we have two high points. And so in this particular distribution, we have two scores, two mode scores that occur most commonly. So the question here is, when is this particular statistic used? It's typically used when we have nominal scales. And recall, we have the four levels of measurement. The first level was referred to as a nominal scale. There are some limitations when using the mode to describe a sample of data, in that if there are more than two modes, it now becomes difficult to provide a description of the pattern that exists in the data. If the distribution has a rather rectangular type of shape to it, and there are some distributions that have rectangular shapes to it, there are many modes. And so in that case, it becomes extremely difficult to interpret the outcome type of distribution. The mode also becomes less of a useful statistic when we deal with skewed distributions that we'll define here in this lecture. And so the next measure of central tendency is referred to as the median. And so as the term indicates, the median represents the score, the dependent variable measurement at the halfway point, at the 50th percentile, where the remaining scores, half of which reside above the median and the other half resides below the median. And there are some unique advantages to using the median. The first is that we can only have one median score in a distribution, as opposed to the mode where there can be multiple instances of scores that occur most often. The median will usually exist where most of the scores are distributed and becomes a very good reflection of the entire sample of scores. And the median is unique in that it's not affected by very high or very low scores that we often refer to as outliers. And the median is most commonly used when we do have those skewed distributions, but also when our data fits within the nominal or ordinal scale of measurement. And so on the left-hand side, what we see here is what's called a normal distribution, and the mode and the median both exist at the same point. The same point is the score around which the highest peak of frequencies occurs for the mode, and that point where half of the scores reside below this point, this particular dependent variable score, and the other half resides above that, thereby defining the median. This becomes a little bit more complex when we look at skewed distributions. And so we label a distribution as being positively or negatively skewed depending upon where the tail of the distribution is. And so the tail of the distribution here on heading in the positive direction would define this type as being positively skewed. And so recall, the x-axis is the dependent variable, and we're measuring the number of occurrences at various levels of that dependent variable. So here we have some very high dependent variable scores. But if we follow and intersect this curve and follow it over to the y-axis, we see that there are only a handful of scores, very low frequency, very low number of occurrences of these very high scores. The mode is still defined as the point where defined by the highest occurrence of those scores at the highest point, the most commonly occurring score. The mean will reside closer to the tail, hence the term positively skewed. The very small number of high scores will skew the mean in the positive direction. Meanwhile, the median will not be sensitive to those handful of very high scores and will reside somewhere between the mode and the mean in any skewed distribution. And once again here, the median is still defined by that dependent variable score to which half of the scores reside below it and the other half will reside above it. Now, in calculating the median, we're looking for the middle value here. And so if we're typically we deal with non-continuous data, so discrete data that can only take on one value, one whole number or another whole number, and usually small sample sizes is when the median is most often used. If we have an odd number of scores, we begin by rank ordering the scores from low to high or from high to low. In this case, I'm going to order the scores from low to high, and the median is the middle score. So here we see an example of 5 scores obtained from 5 different people, discrete, so there are gaps between them. There are no possibilities of fractional components. So we have a person that scored 11, a person that scored 13, 18, 19, and 20. So here we see 3 scores that are very close to each other, 18, 19, and 20, and the 2 remaining scores are quite a bit lower. So we might think that the median is going to be somewhere down here, but that's not true. The median is just the number that is in the middle. Now that occurs with an odd number of scores. If we happen to have an even number of scores, it's still the halfway point. In this case, it's the score that is not observed, but we have to calculate it. So what we've done now we have another sample. Here we see one person on our questionnaire scored a 4, another one scored a 4, a different person scored a 9, 11, 12, and 14. Now, what we need to do here is to find where that middle point here is, but that point that separates the scores in equal lower and upper halves doesn't exist. So in this case, we calculate the median as a fraction of the sum of the 2 scores around which the halfway point resides and divide it by 2. So it's basically an average of the 2 closest middle scores. And in this case, the median will provide a magnitude and location as a representation of an entire set of scores. Perhaps the most common measure of central tendency that's used is something called the mean, or just simply the average. And the mean refers to the score that's located at not the not at the location, but rather a mathematical center. So indicating that if it's a mathematical center, that to arrive at this location, we have to go through some arithmetic here. And so as I indicated, this another term for the mean is the average, and the mean considers all the scores in a distribution. Now, in our equations, x will refer to the raw score of one and only one participant. So if we have 10 participants, we'll have 10 different x scores. X with a bar on top, over top of it. The bar in this video and on this slide seems to be moved over a little bit, but the bar should be drawn directly over the X. This is the symbol used for the mean, the average score for all participants, and it's just simply calculated as the sum. This is uppercase Greek letter sigma as the symbol for the mathematical operation of summation, which means we're adding up everything symbolized through x. And so if we have 10 x's, we would just expand this and say x1 plus x2 plus x3, so on and so forth, up to however many x's we have in our sample, divided by the sample size. And so in our example, if we have 10 participants, we would add up all the scores of the participants and divide it by 10. Now, if we take a look at the normal distribution, and this is a distribution that is clearly defined by the fact that it is symmetrical. So the three measures of central tendency will reside in the middle of the distribution and break it up into mirrored halves. The bottom half will equal the upper half here. And it represents an ideal distribution of scores. So once again, we have a dependent variable. We have a number of scores here. It could be quiz score, could be muscular strength, running speed, so on and so forth. And the measure here on the y-axis is how many people have those scores, and we can see on the very low end, we only have a handful of people. On the very high end, we only have a handful of people, and we call those two regions tails. So we have the frequency value basically tailing off into the positive direction, tailing off in the negative direction. The difference between the lowest dependent variable score and the highest dependent variable score is what we call the range. And we'll define the range once again in the next video when we talk about measures of variability. The single highest score, most commonly occurring score, the single most commonly occurring score, once again, is referred to as the mode. And in the normal distribution, the same score that occurs most often is also the average score and also the median score. Now, the normal distribution can still have a different shape, and that refers to what's called the kurtosis of the normal distribution. So the normal distribution is still symmetrical, but how those scores are distributed does change depending upon the sample that's examined. And so in the blue, we see a very narrowed score referred to as a leptokurtic normal distribution. And if calculated, this will take on a positive value. And in this type of distribution, although it's still symmetrical, we see more of the scores are concentrated around the average, the median, and the mode. So it's a very narrow, and the tails are much longer. The mesokurtic is the normal distribution without without changing its shape. And the kurtosis value for this would be 0. The platykurtic type of distribution will take on a negative value and will be less concentrated around the middle point. So here we see a set of scores that are much more distributed widely than the mesokurtic and leptokurtic distributions. In terms of the skewed distributions, a skewed distribution will only have one very pronounced tail. There's still another tail, but the one tail will be very distinguished here. And so we see the tail very clearly heading in the negative direction, and we see a number of scores existing on the high end. And so if we were interested in running speed, and running speed quantified in meters per second, here we see a small number of runners having a slow running speed. So this is a slow running speed, but if we count up how many runners have a slow running speed, there really aren't that many of them, where we start to see the vast majority of runners having a fairly a more narrow range of running speed. And this is what we call negatively skewed, the tail in the negative direction along the x-axis. And so we have a relatively low number of extremely low scores. An example here is running speed for the 800 meters in the Olympic Games. And so in the Olympic Games, we're dealing with runners that have a fairly narrow range of running speed, and the vast majority of them do, with a few runners that are considerably slower. And so the majority of runners have that similar running speed at the Olympic Games for the 800 meter because of the Olympic standard that runners must meet in competitions prior to the Olympic Games in order to qualify for those games. And on the far right-hand side, here we see the fastest running speeds going from left to right, but we see a very few numbers. In fact, only 3 people would exist at this very small region, and these are the Olympic medalists, which will have the fastest running speed, averaged over 800 meters, that distinguishes them from the vast majority, or from the rest of the runners, placing them at the highest percentile. The other type of skewed distribution is referred to as a positively skewed distribution. And in a similar fashion, we see the tail exists heading in the positive direction. And if we were interested in reaction time, so how quickly a person's neuromuscular system can respond to a stimulus, here we see a relatively low number of extremely high scores. The example here would be reaction time in the 100-meter race, which is at the Olympic Games. So as opposed to the 800 meters, reaction time is not nearly as critical as it is for performing in the 100 meters. You see the vast majority of the sprinters have a short period of time between stimulus and reaction, with a very smaller number of sprinters having a delayed or longer reaction time. Once again, achieving the Olympic standard in pre-Olympic competition will qualify these athletes for the games. And so we would have a fairly narrowed range, a relatively narrow range of reaction time among those athletes. So on this slide, I just want to present an example of how we can view descriptive statistics and how it can actually be, how it can have some very significant implications for some athletes. And so when we talk about descriptive statistics, once again, we're combining scores to form small groups. And we can use a large, but when we deal with a large number of scores, then the distribution will tend to may tend to be skewed, or can also be fit a normal distribution. And so in this case, I'm going to use the example of the National Football League Scouting Combine. This is an annual event that takes place every February in the United States, in which graduating university student athletes, football players, are put through a full battery of physical and mental tests in order for teams to decide who they wish to select in the upcoming NFL draft. And so the question here is the scouting combine an important event? It is a very important event because it precedes what's called the NFL draft, which takes place approximately 2 months later. And so in the NFL draft in 2015, I'm going to use this as an example, there were 32 teams in which in each round, each team in an ordered fashion gets to select a player to invite to their training camp and to sign a contract to joining the team. In 2015, a total of 256 players were selected. Now, I'm going to focus on the first round selections here. And is being selected in the first round very important? What is the implication of being a draftee in the first round? The implication is the signing bonus. That's a one-time payment for signing a contract with the team that selects that particular player. This is different than the salary that the team would pay the player. In 2015, the average signing bonus for the first round selectees was for 32 of them was just over $7.5 million. The standard deviation, as you can see, is almost $4 million. So less than the average, but that's still a pretty large standard deviation. The first round signing bonus median was found to be $6 million. And so we see a difference, quite a fair sized difference between the median and the mean, suggesting to us that this is perhaps a skewed distribution. Now, if we plot the first round signing bonuses per first round selection, here we see a nonlinear decrease in the signing bonus as a player gets selected later and later and later and later in that first round. So the first round selectees is very important to the selectees, because what it does is that the signing bonus is particularly large. And so based upon first round selection, what we see here on the y-axis is the dependent variable. So what's important to note here is that this is not a frequency distribution. We're plotting the dependent variable function of when in the first round those players were selected. And so what we see is that the average was just under $8 million, but the reason we have to focus on plotting our data is because we see only 3 signing bonuses or the mean was only representative of 3 of the signing bonuses. We see that a number of players had much higher signing bonuses. Most of the first round selectees had signing bonuses lower than the mean. So the highest signing bonus went with the first round pick, was over $16 million. That's a one-time payment outside of the salary. The last player selected in the first round was paid a signing bonus of approximately $4 million. So oftentimes the average will not exactly capture each and adequately describe each individual, but it gives an overall picture. So just to summarize the 2 types of skewed distributions and use of central tendency. So the mode is often used for nominal data or data that are distinctively bimodal. If we have ordinal data or a skewed distribution with a ratio with data that fit the ratio or interval category, we would use the median. And the mean is most commonly used when our data adequately approximates a normal distribution that is interval or ratio in nature. So just to review here, the mode for whether we're positive or negative or even normal is still captured by the single highest point on that distribution. The median comes next, while the tails will skew the average in the direction of the tails. So this ends our second video of our Unit 3.